The topic is semiconductor fabrication, top down and bottom up. So my talk is focused on the fabrication, manufacturing of semiconductors, and then until now we are mainly using this top-down method to fabricate a semiconductor structures, but under 10 nanometer, below 10 nanometer, we expect to use a bottom-up approach. So there are several reasons, but the major difference for these two methods are, for instance, we want to fabricate a structure on a substrate, looks like this, okay? Then top-down is to fabricate a structure from a block, okay, like that, and then we can etch down to make this structure. So except this area, all these area will be removed. Then that will be a top-down approach that has been done for fabrication of semiconductors, and bottom-up is to assemble this particle onto here to get to the final structure. Okay, so that's the concept of top-down and bottom-up methods. Top-down methods, it has been studied since 1960s, and then bottom-up method, it has been studied since about 2000 or late 1990s. So this bottom approach is at a very early stage, and then this top-down is a fully established method. And however, under 10 nanometer, now we do not have a tool to make it smaller. Okay, that's the kind of problem. And then also, when we think of a structure of 10 nanometer silicon, for instance, this diameter is 10 nanometer, then the surface of silicon is quickly oxidized in air. So material is not a silicon anymore, it's a silicon oxide. Okay? Then what that means is when we make it very small, we cannot realize the performance of silicon anymore. That's the problem. For the right case, bottom-up case, for instance, if it's nanotubes, then the good thing of a nanotube is not oxidized very well in comparison with the silicon. Okay? So oxidation decrease of a silicon is about 3 to 4 nanometer, but for nanotubes, technically we can remove all the oxygens on the surface. So this one is a more futuristic, but it has a lot of problems in the fabrication. Okay? So we will discuss the manufacturing challenges out there. But I want to start with some of our basic fundamental working principle of a semiconductor. And the material was prepared by a student of my class, okay? Partially. So what is a semiconductor? Semiconductor, that is the material that can control the transfer of charges, electrons, okay? So that's the advantage. And then it's a group 4 material. What that means is we have we have an atom here, like a silicon. Then it has 4 sides for binding. Okay? So if you have another silicon atom, then again this one has 4 binding sides. Okay? So covalent binding happens to make a crystal structure. But that's the group 4 material. And also this material can be, some of the atoms can be replaced with a group 5 okay, one more electrons, or group 3 material, then we can control the charge over this material, then that can enhance the charge transfer, and technically we can control the flow of electrons. Okay, so that's the basics. And on the other hand, also semiconductor is a kind of that means that some of electronic devices having this semiconductor or like a microprocessor. They are generally called as a semiconductor. And let's see the structure of a silicon. So most transistors, they are built on silicon substrate because the process is very well developed, and then we have to start from a very pure silicon material, and then we need a crystal structure to form a silicon substrate. And silicon is a group of material having a 4 remaining binding sites. And then, for example, if we see this silicon, then it has 4 binding sites, and then again, this silicon has 4 binding sites, so it can have a perfect silicon structure. Okay? However, since there is no remaining electrons in there, charge transfer is not that good. Okay? It's a pure silicon. Then, through the diffusion or ion implantation, we can replace one of them. Okay? So, let's say this silicon is replaced with a group 5 material, arsenide. Okay? Then arsenide, it has 1 more electrons. Okay? So that's expressed as a plus. Then this electron is a kind of a remaining electron. So it can help to transfer charges. Okay? It's not a pure material anymore. Okay? So the charge transfer can be enhanced by arsenide, but since we have 1 more electron, it's called N-type. Okay, it's a kind of one negative. So 1 electron makes the whole material as N-type. In comparison with that, silicon can be replaced with a boron. Okay, B. That means it has only 3 binding sites. Then 1 binding is missing in there. That means 1 electron is 1 negative charge. If 1 is missing, then whole thing becomes a positive. Okay? So instead of negative, then we call that as a whole. Okay? And then this material is charged with positive. Okay? So this is a positively charged structure and then negatively charged structure, and this is a single crystal silicon. Okay? So if we diffuse arsenide, then it's negatively charged, and then if we diffuse boron, then it will be positively charged. And in terms of this semiconductor, at the beginning, it started from like a very crude setup, okay, 1947, and then they tried to control the flow of electrons, this crude setup, and kind of the setup, it's similar to current transistor, formed in 1958, and through a more precise manufacturing, like 2 transistors, they were fabricated through the silicon over there. Okay. And in 1971, the first semiconductor chip it was manufactured. At the time, 2,300 transistors, they were assembled, integrated in the circuit. Around the 1970, even though like it's commercially available transistor, people thought it's really kind of challenging to fabricate this kind of transistors in a commercial level because yield was so low. This single chip was so expensive compared to the economy at the time. And since then, the density of semiconductors in a chip, in a single chip, it was increased through this procedure, and then now we are in this VLSI, very large scale integration. So we can integrate billions or like 10 billions of semiconductors in a single chip now. Okay, so we are at this VLSI. Actually, interestingly, 1964, a co-founder of Intel, Moore, he predicted that the integration density in a single chip will be increased every year. Every year, the density will be doubled, okay, with the same price. It was predicted. Actually, you know, some of what the original description is 18 months, but 18 or 12 they are kind of used together. But in the original description, it says every 18 months the number of transistors are doubled. So starting from 1971, every year the number was doubled, and then this is the trend that we go. And then actually, you know, the development of the fabrication process allows us to make it faster. Okay, so within 1 year, the number was increased about like 2.5 times or 3 times. So now we are at here. Okay? So semiconducting companies, they are really compete each other to get to the number, and then the key thing to increase the number of density is the reduction of the pattern size, line width of electrodes. So if you see the directions of semiconductor industries, then you know it's a simple. They want to make a smaller channel, okay, smaller electrode width, and then they want to make it operate fast. So the clock speed is being increased very rapidly, and then they want to have more functionality with a low power consumption. That's why these days a very kind of fast chip is integrated in a small smartphone, right? So we are taking the advantage of this. Then for one of a semiconductor, one kind of semiconductor chips is this CMOS. CMOS is a complementary metal oxide semiconductor. It's kind of one of the names. This is the cross-sectional structure of CMOS. So we have a source and a drain, and in between there is a channel. Okay, so this gate electrode is kind of a passive. Okay, so we can control the flow of electrons through this gate electrode. Okay. So we have a source, okay, and then a drain, and in between there is some of like a semiconductor material, and on top there is a dielectric material like a glass, and on top of that we have aluminum electrodes. Okay. So we will apply electric potential from the source, and then we want to know what kind of a signal will be out. So this one is the source and drain, and depending on the input through the gate, we can make it 0 or 1 at the source. Okay. So that's the structure. And since there is a metal electrode a top, we call this as a complementary metal oxide a semiconductor. Okay, that's the CMOS. Then you know now our interest is how to make it small, squeeze this channel size in order to make it the whole thing as a small device. And this is a kind of a rough diagram how the materials and then structures they are developed at this moment. So in 2003, the Intel they made a 90 nanometer width. 90 nanometer means between this source and drain. Okay, this channel size is about a 90 nanometer. Okay? And then the channel size will be decreased, continuously decreased to 65 and 45 nanometer. And at the beginning, due to the wavelength of light, physics people they predicted that the patterning below 100 nanometer is not possible. Okay? However, through the development of a new wavelength and then fabrication method, they could make it 90 nanometer. And then after that, again, physics people, they predicted under 50 nanometer is not possible. Okay? However, engineers, they overcame the limit of 50 nanometer. And then now they got to about a 22 nanometer this year. Okay? And then I got news that like 17 nanometer will be available commercially in the next year. And again, physics people they predicted that under 10 nanometer is not possible. Okay, but I think they made a feasible idea because this silicon material itself will be quickly oxidized. So maybe below 10 nanometer is not possible. So at this moment, we do not have a specific plan below 10 nanometer. Okay. So these are the kind of plans that are being made by major semiconductor companies. If you see the size of a line width, channel size, then they have a plan go up to 16, 14 nanometer by top-down method. So that's the background of a top-down method. Okay? So let's see a little more details of semiconductor structures, because this structure is very strongly coupled with the fabrication and manufacturing. Okay? So now we will see how to design a inverter. Okay? Inverter means if we give a signal of 0 from here, then we will get the signal of 1. Okay, so this is input, and then if the input is 1, then we will get 0. You know, like an analog scale. This one is technically 0 volt, and this one is technically 5 volt. But now this one was reduced to 2.5 volt or 2.7 volt because they will consume a less power for operation of semiconductors. So now we will design a inverter through the top-down method. Okay. Let's see some of the fundamentals. So in order to make this inverter, we need to understand a P-N junction. Okay. P material is the material is based on the silicon wafer, and P-type material like boron is diffused. Okay, and N-type material that's negatively charged. So S9 is additionally added up to this silicon material. Then this is a P-type material with a lot of holes. Okay, positively charged, and then N-type material is filled with electrons. Okay, and positive material and negative material, and they do not like each other. So there is some of energy barrier. Okay, it's called a depletion zone. Now, we will put this PN junction into a circuit. Okay. Now in this circuit, we will apply some of voltage, okay, to create a current. Then this is the positive side and then negative side. So positive side will go there, then it will push this positive force to this depletion zone. Okay? And then there is no communication in between. And also a negative electrode that will push these electrons, repel electrons by the electrostatic repulsion to this depletion zone. Then under this electric potential, this depletion zone width will be physically smaller. Okay? Then we can make a current. Current will flow, right? Because this depletion zone will be smaller, and then ultimately it can be gone. Okay? This is the other case. Now here is the negative side, and then on the right of battery, that's the positive side. Then negative will attract a force, and then electrons also will be attracted to the right side. Then this depletion zone will be greater. Then current will be terminated. Okay? So this is a PN junction, and depending on the battery polarity, we can control the current. Right? So that's the basic. We will combine this PN junction into a device. If you see this NMOS transistor, then we have a P-type, a silicon wafer at the beginning, at the basis. And then on top of that, we have an N-type material and also an N-type material as a drain. Okay? So now we are trying to make a current through this channel. Okay? And if you see here, then we have a PN junction over there, and then also PN junction over there, right? And also we have a gate. Okay? Now this gate is making a roll. So let's see the details of control over electrons in this NMOS. So we have this N-type material. These two wells, N wells, they are installed in P-type, a semiconductor, a silicon. And there is a dielectric membrane in there, so there is no direct current between this aluminum layer, electrodes, and then P-type semiconductor. So if we apply, for instance, 0 in there, okay? If 0 means it's a negative, okay? So then that means positive will be positive force will be attracted more toward this region, okay? Then this one will be more positive. I would say it's a P plus, okay? And then this source is still like negative. Then the energy barrier, depletion zone will be increased, right? Then there is no current. So when we apply 0 on the gate, then we will get a 0, right? And no current, yeah, no current. And when we apply 1 in here, 5 volt, now we switch it to 1, then the electrons from the p-type material, they will be attracted, even though the number is very small. Okay? So then that means all the source is n, and then channel becomes n, and also this drain is n, right? Then they are the same material. Then there is a current. Okay? So when we make a 1 on there, then that's the current. Okay? So by making the channel as a n-type material, we can make the current. That's why we call this semiconductor as a NMOS transistor. Okay? And then this one is opposite. So if you see the structure, then we will apply a 0 in there. Then 0 means it's a negative. Then you will bring in the positive out there, right? Then P will form. Then no depletion zone. Then current flows, right? Then through the P we can make the current. That means it's a PMOS transistor. And then if it's a 1, then you will attract more of electrons to there. Then it will terminate the current. Then there is no current. So this NMOS transistor is symbolized with this, and then PMOS transistor is symbolized with that one. Now we will combine this NMOS transistor and PMOS transistor, okay, with this circuit. So if you see this structure, then we have a gate, okay, common gate between these two NMOS and PMOS transistors, and then the left over this NMOS transistor is coupled with the ground. That means it's 0. Okay, and then the other side over PMOS transistor is coupled with the 5 volt. That means it's 1. Okay, so yeah, let's see the structure as a whole. So we have this NMOS, and then that's coupled with the PMOS out there, and it's connected with VDD, means it's a 1, and then it's a 0. Okay. Now we will apply one at the gate. Okay. So input is A and output is Y. Okay, Y is there, and we will apply a 0 to the gate. Okay, then let's see what's happening. When we apply 0 out there, then there is no current for this NMOS transistor. Okay, then this one is kind of terminated, turned off, and then only this one is on. Okay, then this VDD is directly connected to this Y, right? Because the current is only on for this PMOS. Then the output is 1, right? And on the other way, if we make the input of gate as 1, then this one is turned off, and then this one is turned on. Then this one is directly connected to 0. Then that means the output is Y. Output is 0. Okay. So this is the inverter. Okay. 0 is input, and then output is 1. So it's reversed, right? And then 1 becomes a 0. Okay. Mm-hmm. This is the actual structure of inverter. Okay. So if you see here, then this is a NMOS, this part, and then this part is a PMOS. Okay. So there is a electrodes with this one. Okay. It's will be coupled with a 0, and then common electrodes. The gate is A is here, okay, and then 2 electrodes in N well and P well that's connected to output Y, right? And then VDD, that's the electrodes out there. Okay, so NMOS and then PMOS, they are combined. So if we give a signal to the gate, then output will come out from there. Okay? So we will see how to fabricate this inverter. Okay? So fabrication process, is kind of a time-consuming. So, but our focus is how many lithography steps we need. Okay? How many mask steps to pattern? Because when we have a pattern here, for example, we have to identify the width over here. Okay? Let's say our resolution of lithography is 1 micron. Then this channel width should be 1 micron. That's the smallest channel width that we can create. Then whole thing will be roughly about 10 micron. Okay? So we will see how many lithography steps we need to fabricate whole thing. So at the beginning, it starts from a silicon wafer and a P-type. So if you see this structure, then the base material is P-type semiconductor. So we will start from the P-type silicon wafer, and then it will be oxidized in thermal oxidation furnace. Then photoresist, it will be spin coated on top. And as you see, the top part was open, right? Selectively open. That means we use the UV lithography to open this window. Yeah, actually, this arrow should go there. Yeah. So that's the first lithography step. The problem is most of the errors in the manufacturing of these semiconductors, that's happening at the step of lithography. Okay? For example, 90% of yield for lithography, then when we fabricate 100 semiconductor chips, then we can get only 90 out of 100. Okay? So we use the one lithography step here, and then we will etch out the oxide layer using this photoresist as a mask. Then we can have a pattern like that. So now we are fabricating this part. Okay? So we need to create a end well through the process. Then photoresist, that's a polymer layer. It can be easily removed in solvent, and then we will diffuse ions into the channel in order to make it as an end well. Even though it starts from a P-type semiconductor, if we diffuse a lot of N-type materials, then it will become an N well. Okay? So through the diffusion, N well will be created by using this oxide layer as a mask. And then oxide layer will be stripped off in hydrofluoric acid, go to the next step. So now we have an N well here. That's this N well, okay, in the whole structure. And go to the next step. So what we will do is we will deposit gate oxide and then polysilicon layer on top, and then do the lithography and then etching. Then we can create this structure. Now this two structure is corresponding to this structure. Okay? So we use the second lithography. If the one lithography step, if the yield is 90%, then we use the second one, so we will have about 80%, right? So now we use the second step and go to the another deposition of oxide layer. And we need a lithography in here in order to identify N well on the left side. Okay? So again, the third lithography was done in here in order to create two wells. Then we will diffuse N-type materials in order to have create these two N wells out there. So now we are at the stage to have these two N wells and then a large N well here, but we have to create these two P wells out there. Anyway, after this step, we will remove oxide layer, and we will go through a similar steps. Okay, I did not draw all the steps. It's kind of a painful to draw all the steps. And then we can identify again P wells inside N well through the lithography. We need another patterning, so it's a fourth. And then we go to the next step to pattern these two oxide layer. That's a fifth step. And then again we will coat the whole thing with the aluminum, and then we will pattern the aluminum to have this aluminum separated out there. Okay, so then that's the final lithography step 6. Okay, if the yield over one lithography step is 90%, then after 6 steps of lithography, we will have about like 50% yield. Okay, yeah. But you know, if for example like my students are working on this process, then they have about like a 5% left after like 6 lithography steps. Okay, because it's quite hard. We have to align the mass very precisely onto this silicon wafer. So each step, you know, the yield is only like 70 or 80%. Then finally, nothing left. Right? Yeah. So let's see. This is the final structure that we fabricated out there. We used the 6 lithography steps, and then if we use the lithography method having the resolution over 1 micron, then if you count all the width over the whole thing, then for example, this one is 1 micron, and this is about half micron, and 1 micron, half micron. If you add up, then we have about 10 R, means R is the resolution. I would say it's 1 micron at this moment. Then it's a 10 micron, and then through out of direction, out of this plane direction, we need a 6R. So we need 60 R square area for this one inverter. Okay? So that's the whole of R's that we can count. And then this structure is fabricated by a top-down method. Okay? And then since 6 lithography steps are involved, yield will be lowered a lot in the process. Now it's a kind of typical inverter that was created by silicon nanowires. And if you see the resolution, then we have to pattern the electrodes, that's a 1R, and then between 2 electrodes we need a gap. Also that's defined by the lithography, that's 1R, and then the third, these electrodes, another R. So 3R by 3R, that's the area, and then lithography that we need is like a 1 lithography step. Okay? So let's see the fabrication procedure. We need a silicon wafer, and then the surface will be oxidized in thermal oxidation chamber, and we need to assemble 2 nanowires, but it doesn't require any of lithography steps. Then on top, we will identify the electrodes, right, with the 1 lithography step. Then we used a 1 lithography step, and then whole structure was fabricated. Only the deal is 2 times of silicon nanowire assembly. Okay, that's a challenging area. Okay? And this is another type of inverter. Okay? So if you see this inverter, then they have a silicon wafer, and then on top is a silicon oxide layer is fabricated on top, and then we have a gold electrodes with about like 20 or 30 nanometer height. That's this gold, and then one singular carbon nanotube is crossed out there. Okay? And on top of that, polymer layer, photoresist was coated, and then that will protect these nanotubes, and then by exposing the nanotubes under some chemical that was made as a N gate, and then this one is a P material. Right. So in this case, we used 2 times of lithography because we defined this electrode first, and then at the second step, we have to define this polymer layer. Okay, so 2 times of lithography, and then through this direction we use the 5R. Okay, define the electrodes gap, and electrodes. That's a 5R, and through this direction only 1R is required. Right? Then total area is a 5R square. And if you see the voltage characteristics, then it's much better than the silicon nanowire. If you apply 2 volts, then it's a -2. Okay, and then if we apply -2, then it goes to 1. So we can make it reversed. It means it's an inverter. Then here we can compare top-down and bottom-up methods. In terms of area, we can make it much smaller. Okay? Fundamentally, the structure itself is different, right? So now we can make it squeezed a lot by 6 times or up to 10 times, right? So fabrication by bottom-up is really promising in that sense. Let's see the next one. The limitation for top-down method now is there are kind of several factors, but now in this semiconductor, I would say the wavelengths are limited. Okay, so that's why we can fabricate up to a 20 nanometer or 30 nanometer at this moment. And for this method, silicon nanowire or nanotubes should be assembled very precisely. Okay? If you see this AFM image, then the gap, orientation of this gap is not perpendicular to this nanowire. Okay? We need to think how it was fabricated. Electrodes was fabricated first, okay, in one direction, and then in a solution there are a bunch of nanotubes. Okay, very high concentration of nanotubes are there. And then solution was randomly dried out on the wafer, and some of them they were deposited like that. But it cannot be perpendicular to the orientation of electrodes, right? And anyway, one is identified. Usually it takes a few days to find out 1 nanowire. It's very weird. Okay, even though randomly they are kind of positioned out there. It's very hard to identify a nanowire onto electrodes. The assembly process is really challenging, right, for these bottom-up methods. And then regarding the lithography steps, this one needs 6 and then 1 and 2. So in terms of lithography, we can make a very high yield. And first, advantage over this top-down is well-established method, and then we'll get to about 15 to 10 nanometer according to our plan. And for bottom method, the structure is very simple, and then fabrication is kind of easy. That does not mean that assembly is not coupled with this fabrication. And cons is assembly process is very challenging, and the fabrication for top-down is very complex. Okay? It needs a very huge facility to make it. And in future, resolution will reach up to 10 nanometer, and then maybe a bottom method will be used to assemble like a 10 nanometer or below range, because we can assemble like a nanotubes or quantum dots or other structures onto electrodes. Okay? So this is a comparison table. Then for the rest of this course lecture, I want to focus on these bottom-up methods. Okay, what kind of methods are available at this moment? So there are like various methods for this bottom-up approach, and then the first one is self-assembly. Okay, and then second is electric field guided assembly. Self-assembly. This one is to kind of mimic the assembly happening in our body. Okay, so for example, when cells are copying another cells, DNA is copied through the RNA, like information transfer. Those assembly process in the cells that was mimicked in this molecular self-assembly. And then there are a lot of working principles. But the thing is, that's dependent on a probability. Okay? So statistics are involved in there, because if the temperature of our body is increasing or decreasing, then those copying process sometimes is enhanced or reduced. Okay? Those a random motion is coupled with this self-assembly. In comparison with that, when we apply a force using an electric field or magnetic field, it's based on a Newton mechanics. Okay? So it can be more precise. So one method based on the probability, and the other method with a Newton mechanics, they are competing at this moment. Of course, physics people, they like Newton mechanics, and then chemistry, they like self-assembly. Okay? So let's see two methods out there. So for a self-assembly, for instance, we can use the charge of materials. So we have a silicon wafer, and then oxide layer was grown on top. On top of that, gold electrodes, it was patterned. And then on top of gold electrodes was self-assembled monolayer was grown. But the monolayer is not grown on a silicon wafer. It's specific to a gold layer. Then this hydrophobic material is likely to be bound with a nanotubes that are coated with negatively charged surfactant. Okay? So nanotube is selectively deposited onto self-assembled monolayer area on top of a gold. Okay? And for the bottom case, the oxide layer, with chemically, it was positively charged like that, and then gold layer, it was coated with a carboxylate. It's a negatively charged ions. Then this negatively charged carbon nanotube, it will like more this positive side, not on this negative side, because charge interaction, this one is attractive, and then this one is repulsive, so it will like more onto that. The thing is, sometimes, even though this negative charge does not like a negative charge, it can stay on top. That's a probability. Okay. So conventionally, the probability of this self-assembly success rate is about 50 to 60%. Okay. It's not that low, but it's not that high. For instance, you have a 1 gigabyte of memory, and then 50% of those memory is wrong, then are you going to use it? No, right? So it needs a very rigorously high yield. Let's see an example. So for the case A means now we want to use this principle, and then for specific case, nanotubes or a nanotube was aligned on top of electrodes, right? So it was preferential, but in certain cases it was kind of a random, oriented perpendicular to the gold electrode. So it was not successful. And the next approach is to make this black area that's positively charged, and then gold electrodes as negatively charged. Then these nanotubes, bright things, since they are negatively charged, they are likely more assembled onto this black area. However, if you see like one nanowire, one nanotube, then it still stay onto electrodes. Okay? So that's it kind of working partially with a probability of about 50 or 60%. That's one of the methods of self-assembly. And if you see this image, then it's more clear. So now nanotubes are negatively charged in DMF, So it's coated with a carboxylate. So it's negatively charged ions. So nanotube is negatively charged, and then left area that's a negatively charged surface, and then right area is coupled with the ammonia group that's a positively charged. So when we have a solution on top, then most of nanotubes are on the positively charged side. Okay? So, however, if you see some of the area, then still you see the nanotubes. Okay? It's kind of compared with this one is almost nothing. However, still we have an errors. And then if you see the range, then it's about like a 5 micron area. It's very hard to scan the whole area. Okay? When we see specific area, the yield looks pretty good, but when we see the overall area, it's not such a kind of a precise. And this one is kind of further developed in order to connect a nanotube between two electrodes. So electrodes were identified, 4 electrodes were identified out there, and then monolayer was grown on top, and the monolayer was removed by electron beam lithography. So electron beam was exposed to remove a specific area, or using an atomic force microscope, we can remove, physically remove a specific area to eliminate this monolayer. Then ammonia group, they were grown on top. So these white circles, that is positively charged, and then black circles, they are negatively charged. And what I mean is nanotubes will like this positively charged area, and it will stay like that. Okay? However, we need a very high concentration of nanotubes in order to the nanotube to recognize this area to be a positive, right? So if you try about 10 of these electrodes, then you will get a success like a 5 or 6. Okay? That's the rough idea. And for this case, also a similar thing happened. So they made they partially removed the oxide surface, and then that was positively charged, and then negatively charged nanotubes, they were aligned out there. So it was better. However, when it's coupled with electrodes, yield was reduced. Okay, so some of the area, it was kind of a blank, or more than a 1 nanotube, it was assembled onto that. Okay? So that's the self-assembly process. And in certain cases, in order to increase the probability, fluid flow, it was combined with a self-assembly process. So if you see here, then there is like a channel, microfluidic channel, and then surface was positively charged, and then negatively charged silicon nanowires, they were transported through the channel. And then due to the shear flow, they were aligned along the fluid flow in the channel. Okay? So they can align the nanowires, and then they investigate how the flow rate will affect the angle or orientation of nanowires. That's shown in this graph. So the variation of orientation is will be reduced by having a higher rate of flow. Okay? And lots of nanowires, they are aligned on a surface. So, and then additionally, they pattern the surface with positively charged ammonia group, NH2, on the surface. Then they could make it like a more precise with fluid flow. So if you see this one, then originally nanowires is like randomly spread out on a patterned surface, but by adding up a fluid flow, they could get a higher yield, right? Because they will increase the probability. So for this case, they use the two times of fluid flow. The first one is this direction, and then second one is with this direction. And for this structure, they use the three times of fluid flow. So first time is this one, and second time is this one, and third time is this one. Then they can make this triangular junctions. Okay. However, sometimes this structure will be made. Sometimes, most times this structure will not be made, right? Because it's the process is still random. Anyway, they could make these crossbar structures, and then they measured a current, and some of structure it was used for demonstration of an inverter. For this future of this self-assembly method is by changing the surface, we can create a lot of interesting structures. Okay? For example, this structure is a polymer, a hybrid structure with a polymer and gold. And then this polymer is more hydrophobic than gold. Then hydrophobic means its charge is neutral. Okay? Then they tend to aggregate each other. And then some of charged gold, they will not stick each other because charge repulsion will happen, and then for this case no charge, neutral, so they will stick together. Then ideally we can make this kind of structure that was attempted in 2004, and as you see this kind of structure happening. Okay. But there are some of holes out there, right? Because also that's coupled with the Brownian motion, okay? And probability out there. Anyway, this kind of a structure could be fabricated, and in very recent years, a few of investigators, they are trying to make a structures with molecules, DNA. Okay, it's called a origami. So they can make this kind of structure by specific bindings, and also this one as a specific bindings. And all the structures, they are made with DNA. Okay, so they can make it like a one by one. At one time, they will make this structure, and then they will make a specific binding with another DNA. So they could control very precisely the structures, and then they could assemble this like a smile shape or like a star shape things. But as you see, they are randomly placed out there, right? In order to use these structures, they wanna assemble all of these structures individually. But the good thing is, for example, DNA or other proteins can be used as drugs. So I think that they are heading for some of the goals, and then one of them is this kind of things. For example, DNA can be assembled in there. Then DNA also is used as a semiconductor to make a light. Then they said, they argued that the DNA can be used as a like light harvesting antenna, and also this one is a kind of box. But technically speaking, there is like still some more projects for this origami, and in the project announcement, they are trying to find a goal application of this structure. But anyway, the method to assemble molecules is being improved a lot. The next one is electric field guided assembly. Electric field means we can create a potential to polarize a particles, okay? Then that can create a force. Okay? So we can have more control over the molecules. It has a pros and cons. So the first thing for the electric field is the electrophoresis. Electrophoresis means it's based on the Coulombic force. So we have charges, okay, charged particles. Then charge-charge interaction will create a force. Then they will get together, okay, or repel each other. That's the Coulombic force. So from there, the final equation that we have is as far as we have an electric field, and then with charged particles, then the charged particle will be attracted. So we have, for example, electrodes, and then charged particles, negatively charged particles, and then apply positive potential on the left, and then negative potential on the right, right? Then this particle will be attracted to the left due to the Coulombic force. Okay? Then the force that is created by this electrophoresis is charged with the strength of electric field. And of course, you know, this particle will go to the left. That's the electrophoresis. And in comparison with the electrophoresis, dielectrophoresis, that's using polarization. Okay? So for dielectrophoresis, we have a particle in there, okay? And then on this particle, it comes with a charge, okay? And then when we apply electric potential, for example, if it's left positive, then negative ions will be there, and then positive holes or ions will be on the right. Then this difference of charges that will attract the particle to the left or right. Okay? In this case, it can go to the left or right. Okay? But it depends on the strength of an electric field. So if you see the force, then in one particle, we have a distance. D means it's the length of a particle. And then if we have a subtraction from the left side of particle to the right side of particle, then on the left side we have the force QE on the left, and then this QER, that's on the right side. And if we subtract to those two forces, then we can come up with the dielectric force. Then when we have a Taylor series expansion and then all the procedures, then we come up with this force. Okay? This dielectric force is proportional to the volume, right? Because polarizable length is increased, then it will increase the force itself. That makes sense. And then second term is the vector, real number of a alpha. So this the whole thing is called a Clausius-Mosseri factor, and in there, if this sign is positive, then it will go to a higher field strength, and if this sign is negative, then it will go to the lower electric field strength. So it will determine the direction of particles in solution. And third thing is a gradient of electric field scale. So we need to create a gradient to move particles. Then the gradient will activate the motion of particles. That's the dielectrophoretic force. Then this is the equation for a spherical particle. Okay? This one is coupled with a volume. And then second parameter, that's the permittivity of a medium. And then this one is the real number of a function of permittivity of particle with permittivity of a medium. And the final term is the gradient of electric field scale. So let's say we have one electrode, large electrodes, and then one small electrodes. Then electric field will be formed like that. Then under this two electrodes, if we have a particle, then that will be polarized. Then if this value is positive, then this particle will be attracted to higher strength of a field because it follows up the gradient of electric field. And if this value is negative, then this particle will go to the left. Okay? Because again, the particle will be polarized, but also solution will be polarized. So in this high the positive value, the particle is more polarizable than the molecules in the medium. Then particle will go to the right. Otherwise, this particle will go to the left. Okay? So that's the dielectrophoresis that has positive and negative dielectrophoresis. So we have done some of the experiment how the particles are moving under an electric field. Now what I show here is it's a channel. Okay, so solution will flow from the right to the left in a microfluidic channel, and then we have a pattern called the electrodes, and we put a spheres, okay, inside. And then when we let the flow go, then particles will be flown, and then they will be attracted onto the edge of electrodes, because the dielectrophoretic force that's highest around the edge. But if you see the initial stage of this deposition, then at a high rate of flow, all the particles will just let go, right? Because attraction force is not enough to attract the particles at the edge. However, when the speed of flow is going down, then they will be deposited around the edge. Right? That's the positive dielectrophoresis. Then this case is for a negative dielectrophoresis. So in the fluidic channel, the flow will go from the left to the right direction, and then this case is for the negative dielectrophoresis. So high electric field strength will be generated around the edge. Then you will repel the particles to the left direction, because particle will be flown from the right direction, okay, from the right to the left to the right. So if you see here, then it cannot cross this electrode edge, because negative force, it will move the particle to the left. And then when we turn off the electric field, of course, particle will be transported to the right direction, right? Mm-hmm. So this one shows a negative dielectrophoresis. Yeah, let's see one more time for this video. So we have particles, they are transported to the right direction, and then because of the negative dielectrophoresis, they cannot cross over these electrodes, but when the electric field is turned off, then they will cross it, right? So these Newtonian mechanics based approach should be precisely controlled to assemble the particles. Any questions? Okay. And then now we will move on to a nanowire. For nanowire, the major difference between a sphere and nanowire, the shape is anisotropic, right? It has an aspect ratio greater than 1. So it has a higher force in one direction. So we will see the electrophoresis first. Electrophoresis is moving by the charged particle on the electric field. And then nanowires, they are charged with a negative. So after deposition, most of nanowires, they should go to the positively charged area, right? Mm-hmm. So these two are the electrodes, and then we will place a solution on top. Now we are doing the experiment under a microscope, and after 30 seconds or 1 minute, we will see where they go. Then negatively charged nanowires, they will be moved, placed onto these positively charged electrodes, right? So they are attached onto that. And the flow here is a kind of random, because without a microfluidic channel, we just put the solution on top. So if you see most of nanowires, they are onto a positively charged electrodes. Okay? So that's the electrophoresis. And then let's see the dielectrophoresis. At this time, we are applying a high frequency to generate a dielectrophoresis. And again, the white area, they are electrodes, and the green area, that's the silicon oxide insulation layer. So if you see, then most of nanowires, they are aligned at the edge where the electric field strength is highest. So they are kind of deposited around the edge, and some of them, they will be crossed between two electrodes, because that's the gap where the electric field strength is the highest, right? So that's the dielectrophoresis. You know, in here, we want to assemble the nanowires very precisely between two electrodes. Then that will be one semiconductor. And then when we divide each electrodes, then those semiconductors devices can be used as individual sensors, and then whatever purpose that we would like to do. That's the bottom-up assembly using an electric field. For this case, we want to try to assemble nanowires on the trench. Okay, so now this area is a blank. It's a cross section, and then on the silicon trench, we have oxide layer with aluminum electrodes, and we will place a solution on top, and then we want to make silicon carbide nanowire span between two electrodes. So on the electrodes, we will place a solution containing silicon carbide nanowires, and then as you see, they were aligned between two electrodes like that. And after 10 or 20 seconds, the solution will be dried out, and these nanowires, they will span between two electrodes. Now, solution is dried out from the outside, and then capillary will adjust the nanowire at the final position. Okay. So these are the nanowires spanned between two electrodes. And this kind of process, actually, you know, I have shown you some of the assembly process having the particle size is like 10 micron, 20 micron. But if you go down to 10 nanometer or 100 nanometer, we cannot see the particles through the optical observation. Then, in that case, this kind of a simulation really helps. So, simulation was done with Wing Camru at Northwestern University. If you see the simulation result, then with a high shear rate, the particles, the nanowires will be transported, but they will just like pass the electrodes because the strength of electric field is not enough to make it down. For medium shear rate, of course, you know, they will be assembled. However, if you see, then some of the cases they can be aligned between two electrodes. However, this one already passed the two electrodes, and very low shear rate. If you see this case, then you know they are aligned between two electrodes. So this assembly process that can be controllable by controlling the external force, flow rate or temperature or electric field strength. And a lot of similar procedure that was generated, and if you see much more like a smaller scale, then this one shows a single carbon nanotube between two electrodes, and then width of electrodes is about 100 nanometer, and then between two electrodes, one single carbon nanotube was assembled. Sometimes debris from a solution that can be also polarized and then assembled between. And this one shows a assembly of a single carbon nanotubes. And then this result was mine. So if you see this electrode pattern, then we have 3 electrodes on the left, and then another 3 pairs of electrodes on the right. And I made about 10 micron gaps. So in one pair of comb, I have 20 electrodes. So total, I have 100 pairs of electrodes, and then assemble the nanotubes out there. So carbon nanotubes, they were assembled between 2 electrodes by controlling the electric field and then fluid flow. So if you see the individual gaps, then one nanotube spans between, but sometimes the kind of a nanotube that is short, it did not span 2 electrodes. So if you count all of them, then yield was about like 90%. And for this case, silicon wafer was used to fabricate 2 electrodes, and then a nanotube was deposited as a bottom of assembly method, and then we have another electrodes to make electrical connection. And after that, the electrodes was separated, then we can have a separate electric response. So these are the fabrication process when we use or other like cells or things. So if you see this DNA is a coiled form, okay, using an atomic force microscope. But when we make a flow in between, then DNA is stretched by a flow, so it will span 2 electrodes. And I showed you the picture of this tensile test device for nanowires. For this case, we have to precisely assemble the nanowire. Then we apply the direct forces to assemble one nanowire. And then also deposition process can be monitored by measuring the resistance in between. So once one nanowire comes in, then the voltage is increased because of this resistance. And then second comes in, then again it's increased, and third, fourth. So we can count how many of them. Then when one comes in, then we can blow out the solution. Then only one nanowire will span that can be tested. And also on the AFM tip, we want to make it more precise. Then nanotubes can be assembled onto this tip. Then it can be used to scan the surface. So compared with just like a bare atomic force microscope image, we can have a more clear image when we scan the surface. Okay? So this is a nanotube onto a AFM tip. And also we can make small fibers with capillary action and an electric field. So in the solution, we have a bunch of nanotubes, and then we will use a sharp tungsten tip to attract the nanotubes, and then when we draw the tip out of this solution, then we can form a fiber, which is this structure. Okay. So yeah, that's all the slides that I showed. Yeah.
Professor, but the problem is when we insert something more on the tip of particular AFMs, we don't exactly know that where is molecule, right?
Where the nanotubes are. Yeah, that's right. So that can be monitored by measurement of electric field, electric resistance or current out there, but it's not visible. So that's why we want to use simulation tools to predict what's happening out there. So usually, in order to develop one process to assemble nanotubes, it takes about like 3 to 4 years. But if you use simulation tools, then that can be kind of reduced to like 1 or 2 years. So that's why experimentalists, they are working together with the simulation people. Yeah. But monitoring, direct monitoring is not possible by itself. Yeah. Okay, thank you.